Well, welcome everyone to today's webinar, Advanced Analytics in Chemistry. We have two presenters today. Volker Kraft, he's our academic ambassador in Europe, and so he promotes and supports the usage of JUMP in academia for teachers, instructors, researchers, and students. And we also have Russ Wolfinger. He's a director actually of the development of JUMP for the life sciences and genomics. And so they're going to be sharing the presentation today. Okay, so with that, I'm going to hand it over to Russ and Volker. I think, Russ, you're going to start. So why don't you go ahead and share your screen to make sure um, that works.
All right. Thank you, Kevin. Can you see my screen okay?
I can. That looks great.
All right.
Oh,
Well, welcome
sorry, Russ.
everyone.
One more thing. I forgot to mention this, folks. If you have questions, type them in the Q&A window. We're going to be monitoring the questions along the way, and we'll be typing in answers. We may occasionally, I may have Russ or Volker stop for a moment to address a specific question because it might be easier for them to show something, but I'm going to type them the answers along the way. If you just want to make a general comment to the audience and us, you can do that in the chat window, but try to keep your questions in the Q&A window. It'll be easier for us to manage. Okay, sorry about that, Russ. You can go ahead again.
No problem. Thank you, Kevin. Yeah, for sure. Make sure you guys get, we love seeing questions in the chat. We want to make sure this is a productive session for you. We are really excited with this topic today because JUMP, as you know, JUMP has just been taking off in throughout universities and academia worldwide. It is really an incredible tool now for teaching and learning across a wide range of topics, mostly analytically related. And then today, specifically related to topics in chemistry. And I will say, I think if we had to poll there's tens of thousands of JUMP users worldwide. And I'd say probably our number one discipline, scientific discipline, is chemistry, which and this spans across all of our major industries. Of course, the chemical industry itself, pharmaceuticals, even semiconductor. There's a lot of nanochemistry going on there now. Consumer products, chemistry is everywhere, as you know. And we are in one exciting time now in terms of deep learning with chemistry. And we've got three great case studies that we want to walk you through today to show off the power and flexibility of JUMP. And then also finishing up with some more modern things that you've likely never seen before. And so we're really excited to share, and we're making JUMP more chemically aware all the time. And these things you're about to see today, I hope will convince you and really encourage and motivate you to kind of give things here a try. For those of you that haven't tried JUMP before, you definitely want it. There's a lot of things on the web, and one good place to start if you're interested in some success stories, we've listed them here in this first link. And you'll notice here we've got a whole range of different nice places where we've succeeded with a lot of our big customers. So please feel free to check these out and drill down on topics that look interesting to you. And of course, make sure to take advantage of that student offer now, which I'm personally so excited that now the JUMP Pro capabilities are included. And we are going to leverage that heavily today using some add-ins that only work with JUMP Pro. So now they also do work with the Student Edition. So you have got access to all the best stuff we're offering, including a lot of the chemistry specific things today. Now, let me mention too, one other place to go visit is the JUMP. If you want to view it like our new app store, where we've got kind of extensions that go even beyond. There's tons of great functionality already in JUMP Pro, and this marketplace extends it even further. And we've got a few of these that we're going to be using today. You see one here listed on the right, the Torch Deep Learning add-in. We'll be using this towards the end to model some chemical data. And I wanted to mention too, while you're here, if you notice, the most downloaded add-ins now, the student menu is number one. I think that was written by our very own Ross Methuselam. And this has got just tons of great content. It's used heavily in teaching using JUMP, so make sure to check that one out. Also, this LearnBot is really great. We are moving into generative AI. And we've got another new one that we're working on and very excited about that'll do coding with the JMP scripting language and almost make JMP itself amenable to natural language processing. So super excited about that. It's very timely and a hot topic right now. And then, as I mentioned, this torch deep learning one. By the way, I've got a side bet going with the developer, this capability explorer. So if you guys got to download. Notice I'm number 4 now. We need to pump these numbers up. So make sure to download this. Have your kids download it. All your friends. We got to get ahead of this. We want to move up to number 3. All right. And then also while you're at it, grab XGBoost. We're going to be looking at that as well. These are kind of the two, Torch and XGBoost will be our 2 main machine learning methods that we'll be using a little bit later. Okay, well, to get started though, we're going to begin kind of with classic quantitative structure activity relationship, a really nice case study. I'm going to pass it over to Volker now, and he'll be walking you through our first case study.
Thanks a lot, Russ. And yeah, I'm happy to demonstrate the first case study, which is about selecting the best material from a high number of material options. And this is actually a case study presented by one of our customers, Procter & Gamble, at a user conference in the past. And they did this selection in a very smart way. So what many are starting with is just a list of available materials. And as you see here, this is a categorical column with many levels, just all the labels of these materials. And we want to find the best material. What is the best material? This is set by 2 responses. So we have a first response, which should be maximized, and we have a second response, which should be minimized. So that's what we are looking for, but the customer did not want to measure the 2 responses on all the material options. Procter & Gamble did the material selection really in a smart way because they built a model to understand what's really driving a good material. What are the properties? And they also wanted to predict if a material is good or maybe even better than the ones in here, if new materials will come in. So this is what I call a sustainable model, which really helps to understand and to make predictions in the future. And this has been done by adding the properties, chemical, biological, physical properties of these materials. And this is also called QSAR, or quantitative structure activity relationships. And this is the quantitative information here. So it's basically a table with numeric properties. And we have this also on the data set. I can just unhide this information. So these are the 19 properties we can use to pick the best material. So let's have a look at these data, these 19 columns. One challenge here is that these properties are highly correlated. So collinearity is really a problem with these data, as you can easily find out with a multivariate platform. High correlation, positive and negative, for many of these columns. So what to do? A solution was to convert or to transform these variables into a smaller set of principal components. And that's easy using the principal components platform in JMP. And one requirement was that the components we are going to use should explain at least 85% of the variation in our data. And as you've seen here, using 6 principal components would explain more than 85% of the variation. So these principal components can be saved and added to the data set by saving them, setting this to 6. And this was already done, so I just cancel the saving of these components, so we have them in here. And the good thing is these are formula columns, so if we would add new materials, more properties, they would be calculated automatically also for new materials. So the goal here at this step is really to limit the data and reduce the dimensions. We already reduced the number of variables or number of columns to 6, but we can only use or consider 12, a maximum of 12 materials, and measure their responses. We cannot measure the responses for all of the 45 material options, just 12. The question is, which ones are the best 12? And here the JMP Custom Designer helps, not building a standard design and swapping all the factor levels independently, but we are just picking materials. We are picking rows based on the principal component data. Yeah, and this can be done by using the custom designer. Yeah, and let me change this. So here you see that the principal components have been added as covariate factors to the design, and then we use the principal component data, all these rows here, the 45 rows, as candidate runs, or better, candidate materials. But we limit the size of the design table, so the number of runs or materials to use, to 12. Yeah, so we can only do 12 materials. And this is the data set here, but before I do this, I can show you the ones which were selected. So I didn't do this live, but we have this column here, DOE, was it used? And now let me select these 12 runs which were selected for modeling. Oops, let me select them, and I set a special color so to keep track. These are the 12 runs, and we can put them on a subset for these data. So that's a smaller data set, the same axis, but we have just these 12 materials. There are two challenges building a model on these data. First, we have more columns than observations. The second is we want to build the model not on the principal components, but on the original data, the axis, the properties. So collinearity is back. We need a robust model. And here, a partial least squares model does a good job. And what we see that for just 6 factors, we can explain above 90% of the variation in the X space and almost 100% of the variation in the Y space. So a principal a partial least squares model has been used, and here you see the diagnostic plot, the first response against the predicted response data using this model, and the same for the second response. So the R-squared is really high. So this looks like a good model, and therefore the model can be saved, or both models for our 2 responses. by saving the prediction formulas. Yeah, we have them in here. So these are the formula columns predicting the two responses, and we can take them over to the original data set. And this was already done here. So we have the same formulas, the PLS models also in here. So now we can really look for the best model. Yeah, and what is not the best model, the best material, of course, and use the model to find the best one. And as you know, as a JMP user, that is the profiler, what you would use here. And here we have the profiler as a script. I can run this. So we see our two model outputs. We see all the settings. I just need to optimize and get the solution. Yeah, and this solution can be saved to the data table by appending these settings, this solution to our table. And that was done. This is this row down here. Let me get this in. And by looking at this multivariate output in the principal component space, we see, oops, this solution, this blue triangle, is really out of our model space. So we are extrapolating here, and that's not a good sign. So we want to bring this back. We want to restrict the solution to be within our model space. And this can be done by adding some statistics, the hoteling t-square, the d mod x, which stand for the distances from the model space, more or less, and adding them to the profiler. And these two should be minimized. These distances, we want to keep them small, yeah, not to go too much away from our main data cloud. Yeah, and that means I should hide this one here. And now optimize again, and we get a new solution. Yeah, and this solution, the restricted solution, can be saved again to the data table. And this restricted one is the row 47. Yeah, and looking at our data again, we see that the green triangle, the new restricted solution, is within our other data. So this looks much better than before. So we can take this model. I hide this again. We can take this model and see what is the best material. And this can be done by a multidimensional scaling. So running this shows our data on a two-dimensional space now. And oops, I should get this in, sorry. We should see the solution. Let me do this again. So here's our solution, the restricted one, the better one. Yeah, and we see that the closest materials we have are maybe material 14 or 18. But we also know that a material here would be even better. So maybe we can also ask our supplier to build such a perfect material for us, at least according to the model. Is this a good model or are we overfitting? So this is an interesting question if you want to predict, if you want to use this model also on new data. So we can look at a model validation because we used the 12 materials for training, building the model, and we can use all the other data because we also have the response data for all the materials. It's a bit cheating, but if we would have them, we could validate and use the other data for testing or validation. Yeah, and this tells us that the R squared on the test data for the first response is 87%, and for the second response, 82%. So that's really promising. That's a really nice model which can be used also for prediction. But is there maybe any other better model than partial least squares? So here maybe you, as a JMP user, you may think about, oh, what about model screening? We can run this and see if there's maybe a better model for our data. Yeah, and this here, this ranking shows partial least squares on the second place for both responses, but it also recommends to have a look into a neural boosted network. In this case, XGBoost is not doing a great job, so that's maybe not an option to look into in the first place. But maybe you also have other data formats. So here we just used tabular data. That's easy, straightforward. But what if your data are text data or smiles, strings, or spectrograms? So in this case, you may require some other machine learning techniques. And that's what Russ is going to show you, some more advanced machine learning tools. I just want to check if there's any urgent question right now.
No, we're doing good, Volker.
Okay, thanks.
All right, thank you, Volker. That's a really great case study. I did want to mention one technical note on that model screening. We caught something in the more recent release of JMP, which is now JMP 19 early adopter, where we noticed that there are some cases where that model screening can be exhibits some so-called leakage. And so if you're going to be doing model screening, I'd recommend using the more modern one, using JMP 19, which is only early adopter version right now, but it will go production this fall. So make sure to do that. And in fact, I'm going to be using that version here now for the rest of the other two case studies, just so you're seeing our most recent code and results. But I really like that. It's really in the wheelhouse of JMP to be able to analyze data like Volker showed, and he kind of definitely navigated you through several of the more powerful features of JMP. And you can get this feel. JMP is not just a coding language. It's not just like an Excel spreadsheet. It really gets you close to your data quickly and lets you get to answers faster and really dive in and interactively explore things. To me, it's kind of unmatched, and it's getting better all the time. So I'm hoping now too, we're going to move kind of historically, QSAR has been around for several decades now for sure. But now it's with these more recent machine learning style methods, it's kind of gotten a new shot in the arm, as it were. And I wanted to walk you through one example of that right now. I'm going to pull from this. I don't know if you guys have seen the Molecule Net data website. This is a great website with several really good examples across different branches of chemistry, where they have different data sets, and even including getting into some quantum mechanics stuff. We're going to use this one here called ESOL, which is a kind of a classic one, just studying water solubility for several common organic small molecules. And we're going to dive deep on that one here in a second. But just to get a preview here, all these data sets are available for free at this website, so I'd highly recommend it. And on top of that, they provide benchmark numbers. And so this also kind of helps you see if you've got an idea for new modeling or a new QSAR approach, you can see if your model's kind of matching up to the benchmarks, and maybe you can even beat those benchmarks. The actual numbers, you can see that there's some different metrics. So we're going to focus on this ESOL one, which is a regression problem. And the metric that we're going to use is root mean squared error. So this classic kind of least squares style error, and smaller is better. So keep that in mind as we go along. And then let's take a look. Let's actually take a look at the benchmarks themselves. So this is another page off of this same website. And if we scroll down here, let's focus on these ESOL results. And you can see here they split the data into validation and test. And of course, the test is usually the one that's the most meaningful in terms of future generalizability. And you can see here they offer a comparison of 8 different models. We are not going to run all, we're only going to run a couple of them today and then a couple of variations. But the two I wanted to draw your attention to are here's XGBoost, which we've been mentioning, and then this one called MPNN, which stands for Message Passing Neural Network. Very interesting new kind of modern approach. So we're going to try both of these in JMP, along with a couple other little twists along the way, and see what we get. And just for reference, notice the RMSE for XGBoost, in this case, just a little bit less than 1 on average. They give some error bars here, and then you can see smaller is better here. So the message passing one has a nice improvement all the way down to around 0.6 for this target. So if you would just kind of keep those two numbers in mind, and let's see if we can match them in JMP and get something similar. So here's the data. Again, this is from a paper by Delaney, and we've got the data loaded into JMP with, and you notice here we've got just over 1,100 molecules. I did want to point out we've got some nice chemical specific functionality now available in yet another add-in, which I didn't mention before. Let me mention it now. It's called, if you search here in the marketplace for materials, you'll see this one called Materials Informatics Toolkit. And this is a really great add-in that it effectively is a wrapper around the RDKit package, which for those of you familiar with it, RDKit's kind of a really great collection of code that just does a lot of different chemical processing. And there's a nice Python. It's typically you'd run it in Python, but this is effectively a point and click wrapper around it as well. And so I'd encourage you to download this one. And it does various things. For example, you can draw pictures, you can create these descriptors, various kinds that are immediately applicable for QSAR, as well as I think it's got a substructure search capability as well. So really well done. It was done by our colleague in Japan, Yuichi, who's a chemist by training, I believe, and he did a great job, I think, with this one. So that's yet another add-in you want to try and add to your toolbox. So I actually use that. That's how these pictures here were drawn using the Material Informatics Toolkit. And then here is the target that we're trying to predict. And then if we wanted to take, we could take if we take the classic QSAR approach, like Volker was just showing, but let's go ahead and use XGBoost this time. And I'm just going to run it here just live. What I've done here in this table is saved an XGBoost script, which you can do, as you know, you can do in JMP. And then this is what you'll get when you run XGBoost. We did a same holdout set that's in the benchmarks. And we did a little bit of tuning on this one. XGBoost actually has quite a few tuning parameters, as you can see here. So it's a little bit daunting at first, but don't let that scare you off. The default parameters are often very well, and then with a little bit of training, you can come up to speed with how these things work. And we also have an auto tune capability. And so once you fit a reasonable XGBoost model, you'll see a training curve as here, and you want it to descend and flatten out. And by the way, we are kind of minimizing mean squared error here. And then to actually compare with the benchmark, let's check RMSE. Okay, we're getting a validation RMSE of 0.7. So if you remember back on the website, the value was closer to 1. So we're already, with just a little bit of tuning in XGBoost, we're already beating the benchmark there that was published. So that's good news. And then of course with JMP, as Volker was showing, JMP's well known for highly interactive graphics and statistics kind of presented to you side by side. And you can immediately see things like here's one molecule. And by the way, I've made the picture of the label, so you can mouse over and see the structure immediately. So these are, to me, really nice capabilities of JMP. We're just kind of popping around the edges here, looking for maybe molecules that weren't predicted as well by the model. And of course, you can drill down and highlight ones and do a more formal error analysis. And then on top of that, we also get this nice table of feature importances, which show which descriptors are the most predictive. So this is super valuable. And this also gives a lot of information in terms of, what properties of the molecules might be most informative. And so you can drill down further. And then one last thing I wanted to mention are these Shapley values, which you can save to the table, and they will break down each prediction into components attributable to each descriptor. And then you can load these then into other JMP platforms like Graph Builder and otherwise to really explore deeply how the model's predicting. So I know one criticism often of these fancier machine learning models like XGBoost is that, it's just a big black box, so complicated, we can never interpret what's going on. I'd like to counter that with these things I've just been showing you, where we can get things like feature importances, which are derived directly from the XGBoost ensemble model, as well as these Shapley values that kind of turn the black box into more of a white box where you can go in and explore exactly what XGBoost is doing and see exactly where it's predicting. You can also do things like profiling and the other nice things that Volker was showing. So this is our first example of using a modern machine learning method to do QSAR. And we're already also beating what they were doing in the paper. So I think already you've got good impetus to try out JMP for this kind of analysis. But we've got a lot more to show. So let's move now to something that I'm super excited about, and that is the idea of using only the SMILES string of the molecule. So now, instead of these numerical descriptors, which are obviously valuable and likely the best place you want to start, but now think about if we just took this SMILES string, a question would be, can we just look at this SMILES string, which for those of you that don't know about SMILES, it's basically a kind of a textual way of describing a molecule. You'll notice the atoms are listed, their symbols, carbons and oxygens, nitrogens are listed, as well as some version of the structure. It doesn't completely describe the 3D structure, but it does give you an idea of where the bonds are located. And so I think it's a fairly standard way of describing molecules now. Here's a relatively simple one. We can see we got 4 carbons, a double bond, and then a 5th one, pentene. And so I think these SMILES strings are really great tools now. And then here's the interesting catch. If we're going to switch over to machine learning now, what we can do, I'm launching now the Torch Deep Learning add-in. Let's take our SMILES string as our input. So instead of our descriptors now, we're going to use just the SMILES string alone, one single column, that's just this text string. We want to predict, we'll put our Y response in that we want to predict, and then let's just do our validation. Like before, let's do a single holdout. And now we can actually use, as a first go, we can use a language model. So to do the prediction. So this is actually a BERT Tiny. And for those of you that have been following the LLM literature, this is one of the earlier, smaller LLMs that was used originally. The BERT stands for bidirectional something transformer. And the BERT architecture is at the heart of all, even the big gigantic ChatGPT, Grok engines now. They have millions of, actually billions of parameters now that consist of these layers that are able to kind of capture language and notice structure and match it to desired targets. And so let's go ahead and try this model. I'm actually running this live now I've just got an older laptop that I do have a small NVIDIA card. And if you are going to get serious into this kind of modeling, I would recommend getting basically, I think the best setup these days would be using Windows with an NVIDIA card. And alas, now that said, though, the Apple Macintosh is also pretty decent, but you may know NVIDIA and Apple don't get along too well. So I don't think you could even get an NVIDIA card in an Apple machine unless you're a total hacker, maybe trying to throw something together. But the typical Windows setup now is can often get it. These cards are fairly affordable, thanks to the gaming world. And so another tip is, if those of you that maybe have a teenage gamer sons, he's probably got a good machine sitting on his desk right now. So you can maybe broker some time to run some of these models, or better yet, get him involved with this as well. It might be something to be excited about. And so look what happened here. That just ran. You can see these are definitely intensive models, so they do take time to run. But it looks like we're definitely getting somewhere here with our predictive model. Let's see what the RMSE is on this one. Okay, it's up around 0.1. So this is worse than the XGBoost model that we were just looking at. However, it is getting somewhere, it looks like. And you can see, in fact, our out-of-fold predictions are definitely picking up signal, which to me is pretty amazing. This model knows nothing about chemistry, just a pure language model. And it's able to parse those smile strings and do pretty well with out-of-fold prediction. So I think already we're kind of boding well for this kind of new approach. And by the way, there's a lot of literature out there. Been a flurry of papers, and that Molecule Net website's got several of these models as well. So if you want to get into this, it's definitely something fun to be learning. But the story gets better. So what we can do next is think about doing a graph neural network on the molecules, where we would, and this is almost to me a perfect match between kind of a mathematical construct and a physical reality, where if we take the molecules themselves, the atoms as the nodes, and then the bonds between them as kind of the edges in a graph, we can then map that to a neural network. And there's a famous one out there called ChemProp, which does this so-called message passing. And so we've got this code loaded into JMP now that you get it automatically when you download the Torch add-in. And this one you can run, if you don't mind, for sake of time, I actually ran this earlier. I did a little bit of tuning, and let's see, this was the first go that I did. And then let me show you the last one. Yes. So I played around a little bit with epochs. I increased it to 200, batch size of 64, which are a little bit different than the defaults. And I got this nice fit. But check this out, RMSE 0.47. And remember back on our website with the results, the message passing test results they got. If you remember here here we go, ESOL, remember it was around, looks like a little bit above 0.5. So we're beating that one just by a little bit. We're down below 0.5 now, 0.47. So to me, this is pretty encouraging stuff. And you can now fit these models with no coding. Just load it into JMP, get your data loaded in, a couple mouse clicks, and you're off and running. So I find this to be super exciting and a really accessible, nice way to do modern style QSAR with these new machine learning models. All right, so that was our second case study. Let's move on now to number 3. And here we've got, let's take a look at yet another, we're going to switch a little bit now and move to spectral data, which, as you know, spectral data has been around in chemistry for decades now. Super popular spectrometry, almost basically a core critical discipline of at least certainly quantitative chemistry, and many different applications. Also, many different kinds of spectral instruments out there, including like mass spec, Raman, near infrared. We're going to look at some NMR data today. And so this is some data we also pulled from the literature. And here's the JMP table, where we've got the basic setup that you want in JMP is to have one row per spectrum. And then you basically set it up as a wide column where the value along the x-axis of the spectrum becomes a column. Each one of these become a column. And then you put the values in kind of horizontally like this, so that the table tends to be wide. If you notice here, we've only got 219 molecules, but over 1,000 columns. So quite wide table. And then just for a little more background, this was a paper by Winning et al. What a great last name, Winning. Gotta love that. We're winning. So this was pulled from the JMR paper when they kindly made the data available. We've loaded into a JMP table, and it'll be embedded in this journal. So if you want to read the background on this particular data set, it's all here and published. The basic idea here is we've got three main compounds that we're mixing: propanol, butanol, pentanol. And the different rows in the table have different proportional values of these. And so this is, in a sense, maybe a bit of a toy problem, but good for sanity checking, and also seeing just how well these machine learning methods work. Spectra are fairly simple by today's standards, but also, again, good just to check, make sure things are working correctly. So this is a great kind of benchmark data set, I think, maybe to try first thing, especially if you've got some new ideas, maybe some new approaches or models you want to try. It's a good one to test on. So our goal, let's go back to the data now. Our goal is to predict the composition of the sample. And you can see here, we've got the three variables loaded up under a group called composition. And you can see the fractions here listed as percentages. And they always sum up to 1 in this case, so it is a mixture. So that's nice. And so one approach we could do, if we wanted to do classic QSAR, we could load these spectral values just directly in to, say, PLS or XGBoost and try to predict directly. That's one good path. I did want to mention a little bit more complicated path that JMP offers called Functional Data Explorer, which you can run. It actually has a lot of features, which we don't have time to get into today, but I would encourage, there's some other content you can find about this. But you can do things like compute wavelet coefficients, you can do peak finding, and it's really a great tool for exploring what we call, in general, functional data, which is in effect like these spectral here, or also you can use it for time series style data. And by the way, again, for sake of time, we've got embedded scripts here in the table that you can run later. So we've got a PLS here that you can try. What I want to make a beeline towards today, though, is this interesting idea of converting the spectra into pictures. And to do that, we're going to compute what are known as spectrograms. Spectrograms are fairly easy to compute. The idea is to use the fast Fourier transform with a moving window, and you just kind of move the window along the spectra and grab the coefficients at each time, and then display them as a heat map. And so we've done that here in the JMP table. And by the way, we've got a utility for creating these spectrograms from raw spectra that comes with the add-in as well. If you notice here under image utilities, we've got a utility called make spectrograms, which you can run and generate these pictures from scratch if you need to, or maybe you've already got them somehow, or you want to compute them elsewhere. But I really like these spectrograms because they kind of give you one single picture to describe the entire row, which, remember, here's over 1,000 data points. You can look at it in one single picture, and you can immediately spot things like, say, there's a blue dot that looks a little bit unusual in terms of maybe exceptionally low, and you can kind of visually scroll along here. But the predominant feature are these big red bands. But now here's the interesting thing, and we're going to use torch again. But now, instead of using the smile string, we're going to use the picture itself as an input. So let's take the spectrogram, and it's going to be our X now, and we'll predict all three compounds simultaneously. And again, let's do cross-validation. And actually, if you don't mind, for sake of time, since time is kind of flying by here, let's just do a single holdout. Let me show you a trick. We typically would recommend you do full K-fold, but if you just want to do something kind of quick, we're going to make indicator columns here. I'm going to use this utility called Make Indicator Columns under the Columns menu. A pen column name, and now we've got these five. We took our original fold column and split it into five, and so now we're going just to use this single one, which just does a single holdout. I'm doing that for sake of time today. We can run this live, and now instead of a language model, we've got image models that we can use, and there's a whole big host of these available for those of you that have been doing machine learning with images. You know, there's been a big area of research. And we've grabbed most of the popular ones now and make those available. You can also download additional ones. But let's just go ahead and run this one by default. And again, I'm running on my laptop here. And you can see this is a very simple model, which isn't doing super great out of the box. It's starting to get there, but you tend to want to tune this a little bit more. And what we'll do for sake of time is just let me run. I've got some results. In fact, what I wanted to show you is that if you change the model to one of these more advanced ones, you can actually get much better predictions. And so we're basically doing image classification now. And by the way, this problem, image classification, extends way beyond chemistry. So if you think about it, any kind of picture data that you've got, and I think, for example, my daughters probably have more pictures on her phone than I've collected my whole lifetime. And so image data is everywhere these days. And so you can now do image classification directly in JMP. This is one great example. These spectrograms, I think, are great ways to do kind of modern QSAR with pictures. But the problem itself actually generalizes quite well. And then to wrap up, this is a wrapper around the Torch library. And so you can save out models, you can generate Python code, and deploy the model themselves in Python. So we're trying to make JMP kind of play friendly with the modern machine learning world, which tends to be Python dominant these days. We've got a few other languages going as well. But to me, very exciting stuff and pretty easy to get to these days. So with that, let me pass it back over to Volker for a wrap up.
Thank you, Russ. Really awesome demonstrations and great to see what's possible today using JMP and Python together. So that's really a dream team, as you could all see. I just want to repeat what we mentioned at the beginning, that if you're academic, a student, an instructor, faculty, or an academic researcher, you can get JMP Student Edition for free. And this provides all the capabilities of JMP you saw today. So it's not just JMP and JMP Pro, but also what you saw today. And that includes the option to add extensions like JMP add-ins for XGBoost or deep learning. We have a few more webinars planned for this summer, and here are the titles and dates again. But you will receive a link to register for these webinars with our follow-up email. And with this, we are ready to take any final questions or feedback. If you have feedback on what you saw today, I think it was really special, a very unique webinar, and the capabilities Russ showed were presented in an academic webinar for the first time as far as I'm aware. So if you have any feedback or any questions, it's the time now to ask.
Yeah, I wanted to mention too, Volker, we're happy to take the conversation offline. If you've got kind of more custom questions that you want to ask about this, we are, as you may have picked up on, we're very excited about these capabilities. They are fairly new, and so still a few rough edges, but overall, a lot of them are working really great now. In fact, we already have customers who have, for example, deployed Python models that they've built in JMP with deep learning, and they're already seeing big successes and gains. So we're in a way, we're kind of just getting started with this. We've got a lot of other things coming as well. So happy to engage with you, and also maybe help you stand up some new content, as I know all this stuff hasn't been kind of formalized into student packages yet, but that's kind of on the roadmap as we move forward. So certainly glad to receive your feedback anytime, and also engage with questions as we go ahead.
Right. Not seeing any specific question right now. I also want to mention again that this is typical JMP, so you get access to really powerful capabilities in Python in using the PyTorch package, but it's all without the need for coding and with really good defaults. So for the hyperparameters, very good defaults are set already, so you can just take them and take a first run, but you can also fine tune and play with all these settings if you like. And again, all without any need for coding or programming in Python.
Yeah, hey Volker, I did want to mention too, for those that are really wanting to dive in deeper, when you download if you go to the marketplace again for the Torch add-in, you can, there is another, I did record another, a related webinar on, here's the Torch page. There's a new, I've got this is another example that I walk through with predicting using smile strings. So if you're interested in some more content, we've got that. And there's also what's known as a Torch storybook, where I think it's up to 47 examples now of different applications. Many of them are chemically related. So I'd encourage you to take a look at that. Let me show you that real quickly here. If you go add-ins, Torch Deep Learning, example data, Torch storybook. There's a whole bunch of new, you can see here several of these chemical examples, and that these are also data sets that you can download and play with directly on your own machine. There's also example output and some benchmarks that you can try. So please do give it a try. Remember too, I got my buddy I'm trying to beat, so need you guys to download this just to get hands on these data alone. It's worth it. So give it a try.
Russ, is that all the resources we have for the PyTorch? There's a question about somebody asking if there's a chapter in the handbook, but the links you're showing, that those are all the resources we have to learn how to use this platform, correct?
I believe, yeah, that's certainly the main one right now. There are a few other video tutorials here. This is the best place to go right now, Kevin. And we are putting some more content together as well. And I've got, for example, I think I may be doing like a workshop at our Discovery conference later this year. So more content is coming and in the works.